Hi, welcome to EE 674. We were discussing the active and reactive power control, and in the last class we discussed the active power control, and we were looking at the single area automatic generation control. And today we will look at the multi-area system, the automatic generation control in multi-area system, and then we will move to the reactive power control. Right, so let's look at the automatic generation control in multi-area network system. Right, so let's consider the two area system represented by the equivalent generating unit, and which are interconnected by a lossless tie line. Okay, so we have the equivalent generator unit. We can represent it as the voltage source with the angle of, let's say, delta 1, and then you have the reactance of x1, and then you have the tie line, right? So let's say tie line, we have a tie line with the reactance of x tie, right? And then the second area, we have the equivalent generator circuit with the voltage E2, and let's say the angle is delta 2 in this case. So both the systems are grounded at this point. Okay, right. So this is the basically the area 1, and this is the area 2, and the areas are interconnected with the tie line. Right, so this is basically the tie line. Okay, so if you analyze this circuit during the normal operation, the real power transfer over the tie line is given by the I would say the real power transfer over the tie line is given by the equation from 1 to 2, area 1 to area 2, P12 is equals to E1, the magnitude of E1 and E2 divided by x12 sine delta 1 2, right, where the delta 1 2 is the angle difference, and the x12 is the total reactance that you can see from the voltage source to the other voltage source, that is V12 is equals to x1 plus x tie plus x2, right? And delta 1 2 is equals to delta 1 minus delta 2, the angle difference, right? So now for a small deviation in the tie line flow, that is the this P12 delta P, let's say we have a small deviation in the tie line flow or the power flow, that is the power going from one area to the other, let's say delta P12. Okay, and from the equation 1 we can say delta P12 is equals to d P12 over d delta 12, right? At the delta 1 to 0. This is the starting point, and then there will be a small change in the angle delta 1 2, right? This would be equals to PS times delta 1 2, where the PS is the synchronizing power coefficient, right? This is called the synchronizing power coefficient. Okay, this is actually the if you take the power and the angle curve, so PE and delta, you know, the power become maximum at the 90 degree, right? P max, and then the curves will look like this. From 0 it increase, and then it becomes maximum at this point, and it drops at 180 degree, it becomes 0. Okay, right? So this is the power angle curve. So this PS is the actually the slope of the power angle curve. Okay, at the initial operating angle, initial operating angle, that is delta 1 to 0. So this is the initial operating angle, that is this, right? So this this point, that means so the you have generator 1 running at delta 1 0 angle minus the generator 2 running at delta 2 0 angle. So this is the initial angle difference, right? So the initial operating angle, and then the PS is the slope of the power angle curve at this point, right? If it's running at this point, so this is the PS, the slope, right? So likewise, right? So we can calculate the synchronous power coefficient, right? PS is equals to d P12 over d delta 1 2 at the initial angle, that is delta 1 to 0, right? Same equation, but we are calculating it at the initial condition. So this would be equals to E1 times E2 over x12 times cos delta 1 to 0. So initial angle difference, right? Right. Okay. So with this condition, you can write an equation for the tie line power deviation, right? So then the tie line power deviation you can write it as delta P12 is equals to PS times delta 1 minus delta 2. So changes in the angle delta 1 and delta 2 times the synchronous power coefficient, right? Right. So now you can see that the okay. So you know that this tie line power flow happens when the the power in the one area is increases, right, and the or the load in the other area decreases, right. So you can say that the tie line power flow appears as load increases in one area and the load decreases in the other area. For the two area network, right. So depending on the direction of the power flow, you can see like which area the load is increasing and which area the load is decreasing, right. uh, and the direction of the power flow it's depend on actually the phase angle difference. If the delta 1 is greater than delta 2, the power flow will from the area 1 to area 2, right. So power flow is from area 1 to area 2, right. And if it's otherwise, the power flow will be in the other direction, right. So okay, now with the block diagram of uh, the the single area, right, what you call it, the automatic generation control, and combining, now we have two areas such that so we will have two such things, and then it is connected to the tie line. So you can draw the block diagram like this. So let's try to draw that. So you can see that the diagram for two area network with LFC which containing only the primary loop. That is, we basically neglect the integral loop that we had over here. So for the time being, without that integral loop, we can draw the block diagram of the two area automatic generation control like this. So right, so you set the for the area 1 you set the reference, right. So delta p reference. Okay, so we will set the reference. So delta, I will take different colors so you can see clearly different parts. So we have delta p reference for area 1, and we have all the blocks that we had earlier for the automatic generation control, 1 over 1 plus tau gs. So here you will get delta p1s, and then the 1 over 1 plus tau t1 is, let's say this is G1 is for area 1, this is T1 is, and then here you will get the delta PM1 is, right? And with that and with the delta PL1 is, the 1 is for basically the area 1, so you can then have to calculate the speed, 1 over 2 H1 is plus T1, right? So this is the same thing that we have done earlier, right? And then from here it comes the 1 over R1, which fed into here, right? This would be minus, and this would also be minus, right? And then you will have the similar system for the area 2. I will draw it in a little bit different color, maybe brown. So I have the delta P ref2 is, so this comes the minus the 1 over R1 thing, and here 1 over 1 plus tau C2 is, so this will be P V1 is, sorry, V2 is, and here you have 1 over 1 plus tau T2 is, which gives delta PM2 is, and here the load change delta PL2 is, one over 2 H2 is plus T2. Actually here you get the delta omega 2 is, and here you get delta omega 1 is, and here you have the 1 over R term, this will be minus 1 over R1. So this is the two automatic generation units for two different areas. Now it is connected through the tie line, right? So you can see that the tie line power flow change will be based on the angle difference. So the angle you can calculate from the here. The change in the speed is represented in change in the angle. So here it comes the so you have to take the difference, so delta 1 minus delta 2, so this would be plus and this would be minus, right? And then you multiply it by ps over s in the Laplace domain, you get the delta, the power flow in the tie line. So this can go in the either direction. One end sees as the load increase and the one end sees as the load decrease. Oops. Right. So for one end it is negative and the other end it is positive. Right. So this is the tie line. So now you have two areas with the automatic generation control connected through a tie line. Okay. So you can actually implement this in a MATLAB or the Octave or whatever you like, or Scilab, and then you can see how the things will act when you change the loads or something like that in each area, right? So you can do a load change, maybe a sudden load change or the slow load change, and see how the tie line power flow will happen, and so, right? Okay, so let's consider a load change in uh, area 1, right? So just to see what's happening. So load change delta PL1 in area 1, right? So let's consider that, and then so in the steady state, both areas will have same steady state frequency deviation. That is delta omega would be equals to delta omega 1, and that would be equals to delta omega 2. So that is delta omega 1 and delta omega 2 will be equal, and let's call it delta omega, right? So now from our load equation, we can say that delta Pm1 minus delta P12 minus delta PL1, even from the block diagram you can see that this is equal to delta omega T1, right? So, and same way the delta Pm2 minus delta P12 would be equals to delta omega T2. There's no load change in the area 2, right? All right. So we can determine the change in the mechanical power. Change in the mechanical power okay. So it is actually determined by the governor and speed characteristic, right? So is determined by the governor and the speed characteristic. Okay, so which is can be written as delta Pm1 is equals to minus delta omega over R1, right? And delta Pm2 is equals to minus delta omega over R2, right? So let's say this is equation 1 and this set is equation 2. So from 1 and 2 we can write that the delta omega is equals to minus delta PL1 over 1 over R1 plus P1 times the 1 over R2 plus T2, right? So we can write this as the delta PL1 minus delta PL1 divided by P1 plus P2, where this is equals to P1 and this is equals to P2, and these are called the frequency bias factors. So the B1 and B2 are called the frequency bias factors. right? Okay, so then we can write the equation for the change in the tie line power. Change in tie line power is delta P12 equals to minus 1 over R2 plus T2 times delta PL1 divided by 1 over R1 plus T1 times 1 over R2 plus T2. Right, so you can derive these easily from the block diagrams and the equations that we have discussed. Right, so the B2, so this is equal to actually B2 over B1 plus P2 times the minus delta EL1. Right, right, so okay, so right, so let's talk about the this how we can control this the tie line the bias, right, the tie line power flow, right? So I would say tie line bias control, right? Okay, so we have considered the load frequency control, or the LFC, right? Equipped with the only the primary control, that is without the integral part, right? I would say for LFC equipped only with primary control loop, right? We have seen that the change of the power in area 1 was met by the increase in the generation in the both area, right? And then there will be the tie line power, right, that is flowing due to the changes in the load, right? So we can write it as a change of power in area 1 was met by one is the increase in the generation in both areas, so the both areas try to correct this through the automatic generation control, right, by the increase in generation in both areas, right? And so which will basically create a change in the tie line power flow, right? So this will change in the generation will create a change in the tie line power flow, and so there will be a reduction in frequency as well, because there will be an angle difference. So and the change in frequency, right? Right. So the challenge here is to keep the frequency at its nominal value, or very closer to the nominal value, which is 50 hertz in our case. So okay, so the idea here is to to maintain the tie line flow, and the change should be supplied by the its the own generation in that particular area, right? So very simple control strategy. uh, to uh, so this is in order to keep the frequency very closer to 50 hertz, right? uh, right uh, so uh, so you can do that by maintaining the tie line flow, and so this can be done through by load change being absorbed by each area, generation by each area, right? Okay. Okay. Right. Right. So the conventional load frequency control, which will be based on the tie line bias control, right? They are what it's going to do is the each area will try to reduce what we call the area control error, right? So in the conventional load frequency control, okay, tie line bias control, right? So where the each area tends to reduce the area control error, right? So it's tried to reduce it to 0, right? So this area control error, or what we call the ACE, the area control error, okay, it's basically the linear combination of the frequency and the tie line error. Like for area I, we can write the area control error as the ACEI is equals to sigma j is equals to 1 to n delta Pij plus Ki delta omega, right? So this is the tie line power flow, right? So and the Ki basically determine the amount of interaction during a disturbance in the neighboring area, right? This basically determines amount of interaction during the disturbance in the neighboring area. Now, how this area will contribute to the disturbance in the neighboring area is determined by this Ki, right? And So typically the the overall satisfactory performance of is achieved when the ki is equals to bi, which is equals to 1 over ri plus di, right? You can say that the overall satisfactory performance is achieved when this is happening, right? So we can for if you consider the two area network that we were discussing, we can write the area control error for two area network or two area system. We can write it as is CE1 is equals to delta P12 plus P1 delta omega 1, because K1 is equals to B1, and ACE2 is equals to delta P21 plus B2 delta omega 2, right? So okay, so now with incorporating the area control error, we can derive the block diagram, right? I will try to get this block diagram that I have drawn earlier and try to modify it. I don't know with my bad. There's a whole lot of stuff, so let me do that and try to get the whole diagram. I might have to reduce the size, get a copy and paste it here. Probably I need to reduce the size. Hope you can see that. All right, okay, let's start from there. So we have the two area control, but now instead of this the reference, we are introducing the area control error, right? So we go and we will also include the integral part of the control, right, which is this case. Let me take the proper color. Ki1 over S in here, right? And the input to this is the area control error for the area 1, and same goes here. So you have Ki2 over S, and the input to that would be the area control error for area 2, right? And then the area control error is calculated from using these two equations, right? So you need the P12 and the P21, right? So you need delta P12 and delta P21. So let's say so here what you have is delta P12, right? So the delta P12 is coming, so here the delta P12, and then maybe I will draw a okay, maybe this, I don't know, right? Right? And then here you have the delta omega 1, right? And then here comes the, so you multiply it by the b1, you get the b1 delta omega 1, right? And then you need to calculate the area control error from there by use of these two, right? uh, so so you are giving the error, so this should be minus and this should be minus, and in the other one the we need p delta p21, so it's minus of delta p12. So when it comes to here, actually this becomes plus, and here you have the b2 times delta omega 2, and so this is minus. Okay, so this is the complete two area control system with the tie line bias and the area control error included, right, in order to achieve the proper control. So when the load changes, whether you can see this, right? So your load is at these 2 points, so the load in the area 1 and the load in the area 2. So you can change the load in the area 1, and you can implement this in MATLAB and change the load in the area 1 and see what would be the effect, and then you can do the same for area 2, change the load in the area 2, keeping the load the load in the area 1 constant, and see the effect. And then you can also change the loads in the different manner, like some stepwise change or slow change or something like that. And then also you can see the changes in both the area load in both the areas and how the system will react and so on. So you can do many experiment with this and get an idea how the two area system will behave with this generation automatic generation control and the tie line bias control implemented, right? Actually I will give you this as one of the assignments, so I will give you detailed information on that. So, and I will also give you some times, maybe like a month or so, like probably after the exams, you can submit the report. Okay, right. So with that we will conclude our discussion on the active power control, right? And then we will move to the reactive power control. Okay.